Hi folks, welcome back to lesson 16 of the Dead Earth game development series brought to you by the Game Institute. I'm Gary Simmons, and in the last lesson we saw how we began to flesh out Jill's hierarchy and add components that are going to be used to feed information to our AI state machine. The AI state machine is going to be the brain of our zombie, and the triggers and the colliders that we added in the last lesson will provide that brain with the sensory input. We also began to construct our animator controller. If the AI state machine is going to be the brain of our character, we can think of the animator as the brain's means of manifesting its will. What we're going to do in this lesson is we're going to design and begin to write the source code to our AI state machine behavior and the various state behaviors that it's going to manage. Before we do that though, what I would like to do is bring up the real Dead Earth game project so that I can show you where the AI state machine lives and show you what it looks like in the inspector and how we use it. I think once we examine where it lives and what it looks like, we'll be able to better understand how we need to develop it. So here I am in the abandoned hospital scene of the real Dead Earth game project, and as you can see in the scene hierarchy, we have Omni Zombie Jill. Now the layout of Jill's hierarchy is slightly different here from how we set her up in our current project, but that's just because while I was teaching you guys, I came up with a slightly better structure and have yet to roll those changes back into this project. Now the important game object here is the AI entity game object in Jill's hierarchy. Remember, this is the game object that moves. It has the animator, it has the capsule collider, it has the NavMesh agent. Let me close all of those up for the time being. And it also has the script that I want to focus on for the next section of this video, the AI state machine script. As you can see, the state machine exposes many properties that we can use to configure the characteristics of the character. We have sliders to control the character's field of view, for example, to control its sight and hearing range. Now you will remember in the last lesson we added that large sphere trigger to Jill. We called this her sensor trigger, and we set it to something quite large, like a radius of 20 meters. Now the sight and hearing sliders that you see here represent the percentage of the total range of the sensor sphere trigger. So for example, if we set the hearing range to 1, its full value, and had a sensor trigger with a range of 20 meters, then whenever an audio aggravator was picked up within the sensor sphere, the zombie would always hear it. I use the word aggravator here to describe any object the zombie considers to be an object of interest and worth investigation. However, if we set her sensor trigger down to something like 0.5, any audio aggravator found inside the sphere would have its distance tested and would be rejected if greater than 10 meters away. The sight slider works the same way, but is used for the rejection of visual aggravators. This allows us to give all of our zombies the same sized sphere triggers if we wish, and simply tweak their senses via the state machine inspector. It's good to have the zombies all with slightly different hearing and sight strengths, so that they don't all react identically to the same aggravators. Now in the case of a visual aggravator, as well as having its distance tested based on the sight slider property, it's also further rejected if it lays outside the character's field of view. To use a simple example, if the field of view was set to 60 degrees, if the visual aggravator was within range of the sensor trigger, but was at an angle steeper than 30 degrees either side of the character's forward vector, it would be rejected. It would not be seen by the character. Now, there are many other properties here that are used to configure the behaviors of the individual child states, such as the health slider, which describes how much health the zombie has left. Each attack would diminish it to some extent depending on the fatality of the weapon used. We also have a satisfaction slider here, which in the case of a zombie basically describes its hunger. When this falls to a low value, the zombie will leave its current patrol route and it will feed on any dead body it finds. While feeding, this property will increase, essentially refueling the character. When this property reaches the top, the zombie stops feeding and resumes its patrol route. Later on, we may also decide to incorporate this property into its final speed so that the zombies that are more malnourished move more slowly, almost like they're too weak to move quickly. The intelligence slider is another interesting property that is used to control how quickly, or if at all, a zombie upon hearing a sound being emitted, is able to determine the source of the sound and investigate the source location. Although it might seem strange, we actually reuse the field of view property in combination with the intelligence property for this purpose. Imagine, for example, a zombie is currently patrolling between two waypoints and a sound is emitted in a building behind the zombie. As long as this sound is emitted within the hearing range of the zombie, this will transition the zombie out of its patrolling state and into an alerted state. In the alerted state, the zombie is essentially turning left or right on the spot, trying to figure out where the target is, in this case, where the sound came from. As the zombie rotates on the spot, if the source of the sound enters its field of view, then we say the zombie has correctly looked in the exact direction of the sound and has figured out where it came from. However, the alerted state has a pretty small timeout, let's say 5 seconds. If it has not rotated to the correct rotation in that time, it will give up and resume patrolling. In the case of a super intelligent zombie, it would simply measure the angle between itself and the source sound, and if found to be in its left space, would begin seeking left. In other words, invoke the turn on the spot left animation. Eventually, as long as it had enough time to do so, it would rotate around to face the general direction that the sound came from and has at that point figured out the source of the sound. However, in the case of an unintelligent zombie, the direction to seek would be more random. Therefore, it might turn on the spot to the right, then back to the left, then back to the right, and never really get to face in the direction of the sound before the alter state times out. We would see the zombie stop, turn left, turn right for a little bit, and then give up and resume patrolling, and it all looks pretty cool. Notice also we have a reference in the inspector to the target trigger. Remember, this is the trigger we added to our Geo object in the last lesson. It exists in Geo's hierarchy, here it is here, and it's the trigger that's going to notify Jill when her capsule collider enters it. Also notice we also have our own stopping distance now exposed. When we set this stopping distance, this essentially just sets the radius of the target trigger at script startup. Now, there are many other properties here that I don't want to discuss until future videos, as they are associated with the Ragdoll reanimation system, which we're not even remotely ready to discuss or add to our AI system yet. But a crucial property I do want to discuss is the current state type property here, as this pretty much describes how the state machine works as a whole. We have already seen that the AI state machine is a mono-behavior component that lives on the AI entity game object. That means it can easily talk to the animator and the NavMesh agent that coexist on that object. The AI state machine contains variables that describe the capabilities and status of the character, and is also the object that is notified of all events, such as when threats are detected. However, the AI state machine also manages a dictionary of AI states. Each state is itself a class, which actually implements the code for that particular state. As only one state can be active at any given time, any messages received by the AI state machine are automatically forwarded to the appropriate functions of the currently active state. This means even using a single state machine, we have the ability to plug in different versions of states. For example, we might write 3 different patrol states and assign them to 3 different AI state machines so that the zombies of those state machines exhibit different patrolling behavior. Now, in this example on screen, we can see that the state machine stores its available states in a dictionary, the key of which is an AI state type enumeration. There are 4 states in this example: an idle state, a patrol state, an attack state, and a seeking state. By default, at startup, we can see in this example the current state is set to be the idle state. Because our AI state machine is a mono behavior, it will have its update method called each frame by Unity. The AI state machine will then give the currently active state a chance to update itself. An individual state can do pretty much anything it wants. The state machine doesn't even really understand or care what the state is. It just knows it has to tell it to update itself. The AI state machine will be notified and keep track of any visual or audio threats, so that the currently active state can query those threats in its update pass and decide what to do about them. An idle state may have a timer, for example, that says, if I have been idle for more than 15 seconds, I think we should start pursuing. The means of changing state within the state machine is shown in this example. Notice when the state machine calls the onUpdate method of the currently active state, that function returns a state. Now in reality this pseudocode isn't actually correct. The function actually returns a member of the AI state type enumeration, and I do it that way so that no state needs to know or hold references to any other states. That isn't what I'm showing here, but this is really just to simplify the discussion. So in the case where the idle wants to remain in idle, the onUpdate function of the idle state simply returns AI state type.idle from its update function. However, if it decided it had been idle long enough, it might return AI state type pursue. Notice how on return from the onUpdate method of the currently active state, the state machine tests the state type returned against the current state type. If it's different, then it's time to change states. The current state's onExecState method is called to give it a chance to do any final cleanup or housekeeping. Then the onEnterState method of the newly returned state is called to initialize the state we are about to transition to. And finally, the current state is set to the newly returned state. In future updates, all messages will now be routed to the pursue state, until of course that state returns a new state to transition to. The state machine will also do many other things in its update method, such as make sure the animator has all the up-to-date parameters it needs. So this looks like a pretty simple plug-and-play solution, simply plugging in the different states that we wish our zombie to support. But how can we assign the state objects to our AI state machine easily? We certainly don't want to hard code a list of state object instantiations in the AI state machine startup function, as that would mean every time we wish to change or alter states, we would need to go in and alter the code of the AI state machine itself. The solution I came up with is to make each AI state also derive from monobehavior. In this case, they don't actually implement any of Unity's magic functions such as update and start. The only object that talks to them directly is the AI state machine. However, by making them monobehavior derivatives, it means that we can simply drag and drop the states we want onto the game object itself, just like we're mixing and matching any other components. It also means that we can have the individual per state properties exposed via the inspector. Now at startup, the AI state machine will simply search its game object for all components of type AI state. Each state will implement a method called getStateType, which will simply return a member of the AI state type enumeration, which gives the AI state machine a key to use for storage within its state dictionary. So flipping back to the Dead Earth project now, we can see the individual AI states that are on this game object. If I close up the AI state machine behavior and open up the zombie idle behavior, you can see that this particular state has an idle time range property that allows us to specify a min and max range in seconds that the zombie is allowed to stay in this state for. Let's have a look at the alerted state. Once again, this contains a single property that allows us to describe how many seconds is the maximum amount of time that the zombie is to stay turning on the spot trying to track its next target. Then we have the feeding state. Now the feeding state doesn't really have any properties that relate to the behavior of the feeding ritual itself, but it has several properties that allow us to assign things like particle systems and the amount of blood that's going to be emitted by that particle system, but we'll see much more on that later on. Then we have the patrol state, which has several more properties, such as whether we wish the patrol to be random. If it's not a random patrol, then the waypoints in the waypoint network that's been assigned to this state will be patrolled in order. But if we select a random patrol, then we can have our zombies picking out any random waypoint to go to next from the waypoint network's list. You can see here that we can specify the speed that we would like the zombie to patrol at. And once again, you're reminded that this is using our speed system. So this is currently set to have a speed of 2, which is the kind of the medium speed of the zombie. And we also have some properties here to do with how the waypoints are processed, but we'll talk more on that much later on when we develop that state ourselves. Then we have the pursuit state. Now this particular state is activated when the zombie has seen a hostile target, such as the player, and is now chasing the player. So it's no longer patrolling its waypoints. And in this particular example, this zombie has been assigned a pursuit speed of 2, but we could set that to 3, and then it would go into a full-blown sprint. But like I said, my different zombies in the level get assigned different speeds between 1 and 3, so they don't all chase after the player at exactly the same speed. and we have the attack state, and the only property this currently has is push speed. Now the attack state is transitioned to when we pursue a target and then the zombie gets within sort of melee range of that target. It then transitions into the attack state where it will begin trying to attack the player by performing one of the attack animations. However, what we also do is we also make sure that while in this state, the zombie is always facing the player and is always kind of slightly pushing into the player. And that's what the push speed is. It just makes sure that if the player is trying to move around, that the zombie kind of pushes against the player so that it isn't too easy to shake the zombie off. So you can see what's really nice about this is because the states are behaviors, every single state can have its own inspector where we can configure the settings. So that's really, really cool. Now, I'm sure you're all itching at this point to start writing some code, but before we do that, we need to have a pretty detailed chat about how these classes are going to be organized. Because the classes that we create in this lesson are going to look a little bit different from the ones I just showed you in the real Dead Earth game. The ones created here will be the most up-to-date design, which I'm going to later roll back into the full Dead Earth project at some point in the future. You see, in truth, Dead Earth was a game that started out very much by accident. It was born out of another project and just something that I was prototyping. Therefore, now that I know the wider implications for the game, I can design it correctly from the start. For example, in the Dead Earth project that I showed a moment ago, you will recall that we had an AI state machine script added to the zombie. The prototype the game was born from did not have any wider expectations for supporting anything other than zombies, and as a result the zombie behavior has been written right into the AI state machine class. We may later want to add friendly NPCs which help the character, and currently in the Dead Earth project this would involve creating another completely separate type of state machine class. Now, while that's not a massive issue in itself, it is going to lead to sloppy fixes and casting elsewhere in the application, when other scripts are trying to register events with the state machine, and it's asking, is it a zombie state machine, or is it a friendly NPC state machine? Now, I'm going to need to go back and fix this limited design later by having a series of abstract base classes that provide a standardized interface to all external modules, so that they can talk to the state machines the same, irrespective of the state machine type. Therefore, we're going to do it correctly the first time in this lesson, and I'm going to roll these changes back into the full Dead Earth project a little later on. So we're going to create an abstract AI state machine class, and then derive more specialized state machines from it. For example, we will create an AI zombie state machine class, and it is this component that will be added to our zombies. Later on, we may decide to create other AI entities that behave completely different from zombies, but they too will be derived from the AI state machine class. This means, for example, that all of our AI state machines can be stored in a scene database together and communicated with elsewhere using their base type. This will free several other areas in our code from having to know specifics about what type of state machine it is communicating with. Although the AI state machine class will be abstract and not directly instantiatable, it will still have any common functionality defined so that we don't have to duplicate the process in each of the derived classes. Now likewise, the individual states used by our state machines will also have a common interface and any common functionality defined in its base classes. Unfortunately, states will need to be more specialized to the exact type of state machine they are being used with. This is because there will be very specific parameters in a zombie's animator that need setting, and therefore very specific properties in the AI zombie state machine exposed to allow for that. For example, any state that is designed to be used with an AI zombie state machine will need to be able to set properties on the parent state machine such as feeding, reanimating, and damage, some of which just wouldn't make sense in the case of a non-zombie AI state machine. Therefore, the AI states used by our zombies will actually have a chain of inheritance. Something like this could be avoided by using generic names for properties in the animator controller, such as parameter 1, parameter 2, and parameter 3, and then have a series of aliases created for these parameters in the state machine. But setting up a complex animator controller using generic parameter names such as this would be extremely error-prone and seems to defy the spirit and ease that Mechanim was invented to provide. So an abstract AI state class will be created as the base interface of all AI states and will contain only methods and fields that would be common to any AI that we implement. From this, we will derive the AI zombie state class, which will contain any functionality common to all zombie states. This will serve as the immediate base class of all our actual zombie states that we add to our game object, such as idle, patrol, attack, etc. Finally, before we start, this is going to take a fair bit of setting up and will involve working on several of these classes simultaneously. Furthermore, we may not have anything that actually runs for a little while until we have all of these relationships set up and established. We will start, of course, by defining the base classes and implementing the base functionality they should contain. We will also need to create a scene management script that can store references to state machines, among other things. You see, most events that happen in Dead Earth will be as a direct result of a trigger or collider message. As we know, when Unity's on-trigger functions are called, or Unity's on-collision functions are called, we are provided by Unity with the collider that generated the message. However, this is usually not the information we actually want. To use an example, let us imagine the player fired his gun, and a raycast was done from the player's position along the line of fire. If the ray hit a body part of the zombie, the player would be provided with the collider that was hit. But what we actually want in this case is the AI state machine of the zombie we hit, so we can tell it that, hey, you've been hit and you should be ragdolled. We often do this by littering our trigger scripts with lots of get component calls to get the actual component we want to talk to. The thing is, these get component calls can be pretty costly, especially when being done hundreds of times for various triggers and colliders that are interacting throughout our level. Therefore, in an AI state machine startup function, the state machine will register all of its colliders with the scene manager so that it can store the IDs of the colliders in a dictionary along with the actual state machine reference. Now this is easy enough to do because every single object in a Unity scene, be it a collider or any other component, is issued a unique ID at scene startup. We can use the unique IDs of our colliders as dictionary keys to store alongside the parent state machine references. Whenever we are given the collider of a zombie via an on-trigger message somewhere in our code and we need to access its state machine, we can simply send the collider's unique ID into the scene manager, which will look this ID up in the dictionary and return its associated AI state machine reference. Now this is a many-to-one mapping, meaning that if the zombie had 15 colliders representing its various body parts, each collider would have an entry in the dictionary with the same AI state machine reference as its value. So I know that was quite a lot to take in, but we needed to have that conversation before we started scripting. So we're going to start now by creating some of the base classes. So I'm going to drill down into my Dead Earth folder and my scripts folder, and I think I'm going to create an AI folder to contain all of my AI scripts. Now we already have one of our AI scripts already created. That's our AI Waypoint Network script. So let's drag that into the AI folder and then drill down into the AI folder itself. And I'm going to create two scripts. The first one is going to be the base class for our state machine. So I'm going to call that AI state machine. And then I'm also going to create the base class for our individual states. So I'm going to call that AI state. Then I'm going to go back up into the parent folder, the scripts folder, and I'm going to create that game scene manager script. So I'll call it game scene manager, like so. And the game scene manager is that script that, well, it's going to manage many things in the scene eventually, but for the time being, we're going to be using it for storing that dictionary. And in that dictionary, there's going to be all of the AI state machines, and they're going to be stored in that dictionary with the collider ID as its key. So every collider of a zombie will have an entry in this dictionary that maps to its AI state machine. So we can very easily get its state machine from anywhere else in any other script if we have the collider. So I'm going to create a new game object in our scene so that I can store that game scene manager on it. So from the create menu in the hierarchy window, I'm going to choose create empty, and I'm going to rename that object game scene manager. And then I'm going to drag that game scene manager script onto it. It doesn't do anything yet, but it's in the scene now, waiting for us when we're ready to do that. And I think the first script I'm going to work on is the AI state machine script. So I'm going to double click on that and open it up in MonoDevelop. So I'll start by getting rid of the boilerplate stuff. I do actually need a start function and an update function, but I prefer to add them when I'm ready. And because this is going to be a base class, we don't ever really want it being instantiated, so I'm going to make this an abstract class. And the first thing I'm going to do up above is I'm going to declare a public enumeration called AI state type, which is going to describe all of the different states that this AI state machine understands. So I'm going to say public enum, AI state type, and then I'm just going to list all the different state types that I can think of, but I can always come back here and add more later. So what else? Attack, feeding, oh, and pursuit. We want a pursuit state, and the zombie's pursuing the target. And I think for now the final thing I will do is have a dead state. We can always come back and adjust these later. So when we create a new state, our state is going to need to return a member of this enumeration in its get state type function. And that's going to allow the state machine to know what the current state is. And if we go back to the real Dead Earth project for a moment, you can see that the current state shows up in the inspector. And because it's an enumerated type, it is shown to us in this nice convenient list here. So we can easily, when we're testing, just set the zombie into different states as well, which is cool. And it also allows us to choose what the starting state is going to be. But it's more than just that. We're also going to use these state types as the key to a dictionary that will store all of the states that are on this game object. So because I'm going to need a dictionary, I'm going to need to use the system.collections.generic namespace. So let me just add that to the top of the file, like so. And then I'll declare that dictionary. It doesn't need to be public, so I'll make it part of my private variable collection. So I will say private dictionary. And like I said, the key of the dictionary is going to be a member of the AI state type, like so. And then the actual value is going to be a reference to one of our AI states. And I think I will call this field states. So I say equals new dictionary AI state type, comma, AI state, like so. And then in the start function, what we'll do is we will search this game object, the game object that this AI state machine is attached to. And for every state we find, we will ask it what state it is, and then we will store it in this dictionary so that we can very easily get the current state from the dictionary just by using the AI state type. So let's go down and define that function now. So I think I'll put this in my start function. So I'll make this a protected function that is virtual so that we can override it in the derived classes. So void start, like so. And then what I'm going to do is ask Unity to give me all of the components on this game object that are of type AI state. So I'm going to need to declare an AI state array, like so. I'll just call that states. And I'll use the getComponents function. Notice the S, not getComponent, getComponents. And the type that I'm looking for on this game object is type AI state, like so. And if there are any AI states or any AI state derived objects on this game object, they're going to be returned to us in this states array. So let's now iterate through all of those states and check that they're valid. So I'll say for each AI state, state in states, like so. And inside there, I will say if state doesn't equal null, and what I need to do is I need to make sure that our dictionary here, called states, doesn't already contain an AI state that has this same AI state type key. In other words, if there's already an idle state in our dictionary, we can add another one. Our state machine doesn't know what to do. Each state has to be a unique AI state type. So to do that, I will use the state dictionary's contains key function to check if there's already a state that has the same key, and if not, then we won't be able to add this state. So for that I will say and if states contains key, actually I'll say if not states contains key. We want to step into this conditional code if the key doesn't already exist. So what are we going to send in as the key? Well, we haven't written it yet, but our AI state class is going to have a function called getStateType, which is going to return a member of the AI state type enumeration. So the key is going to be the current state that we're processing in this iteration of the loop, get state type. That function does not yet exist. Need another bracket on the end there. There you go. So now we need to assign it to the dictionary. So we say states, and once again we'll use the states get state type function. Remember, this is the key, and we'll assign that the actual state. So just to recap, in case you're not really used to using dictionaries, we're saying give me all of the states on this game object, and then we're going to loop through each of those states and examine each one at a time. And while we're iterating this loop, the current state that we're examining is called state. And we say assuming it's not null, and assuming our states dictionary doesn't already contain a state that is stored in the dictionary with the key of this state type, then store in the dictionary with a key of this state's type the state. So let me just pause the video and put some comments on this so it will make it a little easier to read. Okay, so what I'm going to do now, because I absolutely hate seeing get state type in red, is I'm going to open up the AI state class, and I'm also going to define that function in its interface as well. So we're going to be working on both of these classes together. So if I go back to Unity, open up the AI state class, once again delete all of this stuff here, we don't need it. We do want our states to be derived from monobehavior so that we can add them to the game object. And what I will do for now is I will just add that single method, like so. As you can see, this is an abstract method. It has to be abstract because we can't possibly in the base class put anything about what state type it actually is, because that's the very thing that we're going to want to change on a per state basis when we derive classes from this class. But that should be enough to at least allow me to stop getting that error in my AI state machine class. There you go. So at least now our state machine knows that that function exists. Let me put some comments above the start function a moment. There you go. Let me just check I'm not getting an error there. Oops, I am. I'll tell you what that is. I must remember to make my AI state class abstract as well. We certainly don't want our AI state class ever being instantiated, as it's not going to have all the code it needs to be a fully functioning state. Remember, this is just the base class of states that we're going to derive from it. So the next thing I'm going to do is create another public enum, and I'm going to call this AI target type. Now, the way that the AI system works is we have this big sensor sphere trigger, which is on the AI trigger layer. And there are going to be various objects, which I call aggravators, that are going to be placed throughout the level. The player is an aggravator. Certain sounds can be aggravators. Dead bodies can be aggravators, and so can other things too, like lights can be aggravators if we wish them to be. And when any of these objects enter the zombie's sphere sensor trigger, it's going to call the AI state machine and notify it that, hey, I'm a potential target. So we need to store these targets each frame so that the current state that's being processed can make a decision about whether this is a state that is worth pursuing for the zombie. So in order to identify the type that it is to the AI state machine, we use this AI target type. Let me put a capital in there. And I always put none in the first member just so that I have a way of distinguishing if something's not working properly. If it's set to none, then something's going wrong, because it never should be. There are certain target types which aren't aggravators. For example, a waypoint will also be a target type. When it's time to go to the next waypoint, the patrol state will grab the next waypoint from the waypoint network, and it will make a target from it, and it will say to the state machine, hey, this is your next target type. So our first target type is going to be waypoint. Now don't worry too much, you're going to see how this is all used in a moment. I just need you to understand that what this is describing the types of things that can be targets for the AI state machine. And they fall into two categories really, visual targets and audio targets. So the first type of visual target is the player. That's the most high priority visual target. And another visual target is a light. Not all lights, just lights that we put certain triggers on that we wish to stimulate the zombie, such as the player's flashlight, for example. What's really cool about lights being stimulus for the zombie is that you could have a situation where, let's say the zombies are in a different room to you. You could walk into the room next door, turn a light on, and then all the zombies in the room next door would all stand up and go like, ugh, what's happening? And you'd be going like, oh God, they're coming. And it would be a frightful experience. Or not. And the kind of lowest priority visual threat is food, which is really just a dead body. I mean, we can make it anything we want, but at the moment in Dead Earth, any dead bodies lying on the ground are classed as visual food. And this is the lowest priority target. In fact, the zombie will only set this as a target and override the current waypoint as its target if it's very hungry. So I'll call that visual food. And the final one we'll do for now is just an audio threat, which I just call audio. And the great thing about audio threats is we can have zombies do things like react to the fact that the player has fired the gun, which has made a sound, and then all the zombies in a certain location will start to look around and see where that's coming from. And of course the player can also use that in the strategy of the game. So if the player is trying to get down an alley or something and it's blocked with zombies, what he could do is he could go and find a car, bang on the car with a crowbar, set off the car alarm, and all the zombies go to investigate where the sound is coming from. So that's the general idea of what the audio target type can be used for. So we really need to create a support structure so that when any of these targets do come within range of the zombie's sensor trigger, when it notifies the AI state machine, it can pass in lots of useful information about the type of target it is and other information such as its position in the world and perhaps in some cases its collider. So I think I'm going to create a new public struct for this purpose, and I'm going to call it AI target. Dun, dun, dun. So let's think about some of the things we may want to know about a target. Well, first of all, we're going to want to know what its target type is. So we'll give it an AI target type member. We'll call that type. The next thing we're probably going to want to know, at least in places where it's applicable, is its collider. Let's store a reference to that. And of course, it also wouldn't hurt, would it, knowing the position of the target. So let's make a vector3 member called position. And we'll also store the distance to the target as well. That can just be a float. And if this particular struct is being used to describe the current target that we're heading towards, instead of just one of the potential targets that we may select, then this distance value is going to be always getting updated each frame by the AI state machine, so it correctly reflects the distance to the target from the player's position. And finally, I'm also going to add one more float called time. So that's going to be pretty useful whenever a target is in our sensor trigger. We're going to keep its time updated so that we know when we last saw it, because there's certain things where the zombie is going to go and see if there's anything at the target, and once a certain time elapses, it's going to say, hey, there's nothing here. I thought I heard something, I thought I saw something, but I was wrong. And I'll put some comments in there to make it a little bit more beautiful. So the reason why I've made all of these members private is because whenever we have instances of AI targets being maintained, they contain pretty crucial information, and therefore I want to control access. So what I'll do is I'll create some public properties, just simple getter accesses, and then what I want to do is I want to create a set function that is going to actually set the properties. And I like to do it that way for really important things like this, so that I know that when I really want to change something important, I'm calling a function, not just assigning a property. So I'm going to add a public getter for the type called type, and of course that will just simply return the underlying type like so. And then I'll create a public getter for the collider. Once again, this is just going to be a getter that returns that collider reference. I'm also going to create a public getter for the position. The distance property is actually an exception here. For reasons that will become clear, I will actually want to update the distance quite easily without specifying all of the other data, so that we keep a track of how close we are to the target. So I'm actually going to do a getter and a setter for that, like so. And time also just needs a read-only accessor. So once again, a public float called time that simply returns. So because all of the members of this structure are private at the moment, we're going to need a public setter function. So I'm going to create a public function with a void return type called set. It's going to take as its parameters an AI target type, T, a collider, C, a position, which is going to be a vector3, P, and a float that is going to contain the distance. Now notice how we don't pass in a time. You see, every time we wish to set the information about a target, you're going to see later how when we do that, we really want to record the time at which the target was set. That way we can determine later on if a target has been set for such a period of time that it's now timed out and the zombie essentially loses interest in that target. The best way to do that is when we set the target information to just use Unity's time class, and in particular the time.time property, and assign it to the time value inside the set function. So let's now copy those parameter values into the actual class members. So we're going to say type equals T, collider equals C, position equals P, distance, I bet you know where this is going, equals D, and then for time we're going to assign it the current time, which we're going to use Unity's time class and its .time property for that. Now you're going to see later how the AI state machine is actually going to have three properties of this type, of type AI target. One is going to be always containing what is the most high priority visual threat, another the most high priority audio threat, and another one that is going to contain the actual target that is currently set, the thing that we're heading towards. Now these are all going to be set by the child state that is running, and we haven't implemented the child states yet, so you just have to take my word for that until you see all of this working. The point being here though is that because this is a struct, we don't want to delete and renew, we just simply want to clear it each frame, because every single fixed update our sensor trigger is going to be getting bombarded with the latest up-to-date information about the threats. So the current visual threat and the current audio threat will always be getting overwritten. So each tick of the physics system, and we do this in the physics system because obviously this is all to do with the interactions of colliders which are processed in the physics step, we want to just clear all of the information out of these targets. Not out of the actual target that we're using, but out of the visual threat and the audio threat. So we're going to need to create a public clear function. Once again, it's got a void return type, takes no parameters. And it's just going to set all of these things to kind of sensible default values. So we'll set type to AI target type none. We'll set collider to null. We'll set the position to vector3.0. And we'll set time to 0. And we'll set distance to something really big, so we'll use mathf.infinity there. So there you go, we have a self-contained AI target struct now that we can store information in about a target, and we can also clear when we wish to reset all of its values. And like I said, we're going to be sort of doing this in the fixed update method of our AI state machine, so that at the beginning of each physics step we clear any data stored there, giving Unity's physics system a chance via its on-trigger functions to register the up-to-date threats each frame. And then the current state that is running can assess those threats and decide if any of those should become the current target. Now I've made a mistake here. You'll notice at the beginning I set my dictionary of states here to be private. Really, we don't want any of this to be private. We want it to be protected, because remember, this is a base class and we're going to want to have the derived classes have access to all this. So I'm going to set all of this stuff to protected, where I would usually set it to private. So now we have our AI target structure. I'm going to declare two public variables that are going to contain the audio threat and the visual threat. And like I said, these are going to be set by the actual state that is running, but they're stored up in the state machine so that if we're transitioning between states, we don't lose the information that state might have calculated. In other words, just say for example we decided to store the visual threat in the current state that was assessing it. If we then said, hey, this is a visual threat, I now want to go into attack mode, when we transitioned out of that state we would lose that information because it's stored in the state which is no longer active. So that's why we use the AI state machine as a kind of place to push some information that needs to cross state boundaries. So this is going to be a public AI target, and I'm going to call this visual threat, like so, and I'm going to create another public AI target again, and I'm going to call this audio threat. And we're not going to be seeing these getting used for a moment until we start creating the actual child states that the state machine is going to execute. And now I also want to create a third AI target type, which is going to contain the information about the current target that we're heading towards. So I'll make this protected as well, and this is going to be called target. So why did I make these public and this one protected? Well, I don't want any state to ever be able to directly set the actual target, because setting the target information for the state machine isn't just a case of setting this data here of our AI target class. There are other things involved which need to be encapsulated in a state machine method. For example, if I go back to our Unity editor for a moment and zoom in on Zombie Jill, you will remember that in her hierarchy we have this target trigger which we're going to be using to notify us when Jill enters her target sort of radius. So when we set a new target for our state machine, we don't just want to set the target information of the AI target type, we also want to at the same time set the radius of this sphere and position it over the position of that target. So that's why we need to create a method of the AI state machine, so that when a child state wants to set a new target, it calls this method, which also sets up this sphere and positions it in the world. So we're going to need to create some other protected members, because at the moment we haven't got any means of assigning both our target trigger and our sensor trigger, that's the great big one, to our game object. So let's declare two protected members that allow us to make that assignment, but we want them to show up in the inspector, so we'll make sure that we use the serialized field attribute. So I'm going to say serialized field. Once again, we want these to be protected so that nothing outside of a state machine can meddle with them. And of course, both of these triggers that we want to have references to are sphere colliders. So sphere collider. I think I'll call this one, this is going to be the one where we assign the reference to our target trigger. So I will call it target trigger, like so. Set that to null by default. and we'll do the same again so that we can store a reference to the sensor trigger as well, and I'll call that sensor trigger, why not, and set that to null by default as well. Now while I'm here, we also know that our game object is going to have several other components attached to it which we're going to want to cache, things like the animator, the nav agent and things like that. So let's create our component cache here. So I'm going to want a protected member of type animator. I'm also going to want to cache a reference to the nav mesh agent as well, because I'm sure some of my child states may wish to talk to that from time. I'll just call this nav agent. Set that to null as well by default. I also want to store a reference to the capsule collider that's on our game object. Remember, that's this one here that actually sort of defines the shape of Jill's body and is the thing that allows us to know when our zombie has entered a trigger, such as its target trigger or its melee trigger. So I'm going to make that another protected member of type collider, and I'll just call that collider. I'll know what that is. It's the only collider on this particular game object. And I'll probably also cache a reference to the transform of this game object. Now that's not really necessary in Unity 5 because the transform property is a special property of MonoBehavior that is already cached, so it isn't doing an expensive component lookup. But I'll cache it anyway just for consistency, and at least I'm saving myself the minuscule overhead of doing that property read from a property function call. So I'll set that to null as well. And I'll hook all these up in the awake function. I like to do component caches in the awake function, but then I like to configure the individual scripts when I know they have all been constructed and set up properly in the start function. That's just my personal preference. And I think probably some of our child states are going to want access to things like the animator and the nav agent. So I'll make some public accessors for those, like so. As you can see, they're just getters, not setters. So I think the next thing that I'm going to add is going to be a stopping distance property. Now I know the nav mesh agent has its own stopping distance property. If we go back to Jill's AI entity object, we can see there it is. There's the stopping distance. We can't use this anymore because we're just completely ignoring what the nav agent is telling us to do velocity wise. So we might as well just set that to 0 and set auto braking to off. And then we've got total control then over when the nav agent reaches its destination, when it enters that target trigger that we've set up. So we're going to want a stopping distance inside our own AI state machine. And when we set a target, and remember I said that when we create that set target function in a moment, it's also going to set this sphere collider in the world. This is the target trigger. And it's also going to set its radius. So what is it going to set its radius to? Well, it's going to set its radius to the stopping distance that we set. So we're going to want that stopping distance property defined first so that we can use it in our set target function. Once again, I want this to show up in the inspector, so I'm going to make this a serialized field. And also, I don't really want this to just to be a float. I want it to be a nice slider bar. And Unity has some pretty cool attributes that it understands that we can add to variable declarators. And the one I want to use now is called the range attribute, where we specify two numbers in the parentheses separated by a comma to describe the min and max range of the value. And then when this is rendered using the default inspector drawing mechanism, it won't render this as a sort of a box with a float number in it. It will actually render it as a slider, which is really cool. So I want my stopping distance to say, I don't know, between 0 and 15. So I want to make this a protected member. It needs to be of type float, and I'll call it stopping distance and set it to I'll set it to 1 by default. We don't want our little target trigger having no radius, do we? Put a line between those so that I can have all the ones that have this range attribute in the same group together so that it doesn't make it look too messy. Okay, so what we want to do now is we want to create our set target function. This is a function that one of our child states is going to be able to call that will tell the state machine, hey, this is the target I want you to set. And what it will do is it will copy those values into our AI target structure here, but it will also resize and reposition the target trigger. So I'll create that under my start function, and this needs to be a public function, void return type, and we'll call it set target. Actually, I probably want to create a few overloads. So the first one I'll create is when we have the individual information, such as the type and the collider and the distance, etc. And we just want to send those in as separate parameters. So we'll say AI target type T, collider C, position P, which is a vector 3, and finally the distance D. And the first thing that will do is it will just call the set function of our target member. Remember, this target member is this one up here, which is of type AI target. Okay, so we're just going to set all of the information for our AI target type here using this set function here. So we're just passing the information straight along. So we'll do target set T C P D, like so. And we also know from when we wrote that set function that inside that function it's going to automatically record what the current time is. Now, the reason we couldn't make this target member public and just allow our states to call the set function directly is because whenever we set the values of this target, we need to also reposition and resize the target trigger. So let's do that now, assuming of course we have a valid reference to a target trigger. So I'll say if target trigger doesn't equal null, then we say the radius of our target trigger. Remember, target trigger is a sphere collider, and we set that to our stopping distance property. And then what we get is the transform of the target trigger and set its position to the position of our target object. And then we enable the trigger because it may be disabled. We only have it enabled when it's being used. So that now will correctly move that sphere collider here, our target trigger, whenever we set a new target. Now I'm going to create another version of this set target function so it's overloaded so that we can use it in situations where we already have all of the information in an AI target structure and we just want to pass that in. So rather than painstakingly type it out, I'll just paste it in here so you can see what it looks like. As you can see, it looks almost exactly the same. Instead of passing in the individual parameters, however, we just pass in an AI target. We directly assign that to our target member, and then we do exactly the same as we did above. We just configure our target trigger, its radius, its position, and then enable it. I think finally what I'll do, now I'm not using this in Dead Earth at the moment, but I'm going to do it anyway because I think I might need it in the future, is I want to do probably an overload of this set target function that takes an additional parameter that allows us to override the stopping distance of the parent just on a per target basis. So if for whatever reason there was a state that wanted to be sensitive to something that nothing else was, and it was like a really big thing we wanted to set the target around, we could call that function and we could specify a kind of stopping distance override for just that target. So what I'm going to do is I'm going to just copy the one we've already got and I'll paste it underneath. I'm going to put some comments on these in a moment, so don't worry about it. And I'll pass in the additional float, and I'll call this S for stopping distance. Once again, we just pass in the values into the actual target structure as always, but in this particular case, we don't use stopping distance. We set the radius of the trigger to S instead. So we now have the functions that we need, and several of them, so that we can set the details of the target and we can also configure its trigger. But we also need a function that's going to allow us to clear this target as well. We can't just do target.clear, we also need to disable the target trigger as well. Otherwise, if we just leave that trigger in the level, our zombie might eventually walk through it and think that it's arrived at a waypoint or something like that. So we definitely need to be able to clear a target when it's no longer in use. So this is once again going to be a public void return type called clear. It's going to take no parameters and it's just going to call the target clear function like so, and then it's going to say assuming we have a target trigger, then we just want to disable it. We want to make sure that it's not enabled. So we set its enabled property to false like so. So as we've created our targeting system now, we might as well create our fixed update while we're here. And that's going to be really simple in the base class. All it has to do is simply clear the audio and visual targets each frame and recalculate the distance to the current target. So we're going to make this function once again protected virtual void, so it can be overridden if we need to, but I don't think we're even going to need to override this in the derived class. This is how simple the fixed update needs to be. So we're going to say protected virtual void fixed update. And I'm sure you know this by now if you're in this course, but this is the function that is called by Unity with each tick of the physics system. And it's simply going to say visual threat dot clear and audio threat dot clear. So the visual and audio threats are going to be cleared each update. And the child state that is running is going to be notified using a system that I'm going to show you in a moment whenever a new trigger comes into our sensor range. within the given update, and then it can decide what to do. And the idea is that at the end of the update, the visual threat and the audio threat will contain what that state considers to be the highest priority threats. And the state may have also set the target as well, if it decided that one of those threats was worth overriding the current target for. So really all the fixed update function has to do is just check that if we have got a valid target, so we'll say if target.type doesn't equal AI target type.none, like so, then calculate that target's distance from this character. Remember, this AI state machine is on our character, okay? So we're basically calculating the distance from ourselves to our target. So we'll say target.distance, and now you can see why we needed the distance property of our AI target struct to also have a public setter equals, and we'll use the vector3 class's distance function for this, which takes two positions and calculates the distance between them. The first position will simply be our position, the position of our transform, and the second position we wish to measure the distance between will of course be the position of the actual target itself, so target.position. And that is pretty much all the fixed update function has to do. It just has to keep track of the current target and the distance from it, and it also has to just make sure that the audio threats and the visual threats are cleared each frame. So let me now add a new member of AI state type to our AI state machine, which is once again going to be serialized in the inspector. So I'm going to use that serialized field modifier, and I want this to be once again a protected member of AI state type, and I'm going to call this current state type, and we'll set this initially to AI state type idle. So this is going to be the default state that our AI state machine is going to start off in, but this is going to show up in the inspector, so we can always change this in the inspector to change the initial state that this state machine starts off in. So if we wanted to, in the inspector we'll be able to set this to patrol, so a zombie would start off immediately in the patrol state. And this is also going to be set in our update function when we're changing from one state to the next, so this is going to be also something that's pretty good to watch from a debug standpoint, so that we can check that all the transitions are happening correctly. And I think what I'm also going to do is create my awake function here as well, because remember I said that we have these components here that we're going to cache in the awake function, so we might as well do that now. So once again, I want the awake function to be a protected virtual function so that we have access to it from any derived classes, but we can also override it in the derived class. We know what this function looks like. It's called awake with a capital A, and this is really now just going to cache all of the components that are on this game object. So I'll start with the transform, then I'll do the animator, and for everything but the transform we have to do those get component calls. So I want to search for a component of type animator. We're also going to search for the nav mesh agent. So what's our variable called? Nav agent. And I say get component nav mesh agent, like so. And finally I want to cache our capsule collider that's on our character. So I'll say collider equals get component type collider. Doesn't matter whether it's a capsule collider, it can be any collider. Oh, what have I done there? Made a right mess of that, didn't I? There you go, that's better. And then what I'm going to do before I continue is I'm just going to pause the video and I'll put some comments on some of this stuff, okay? There you go, so I've put a lot of comments in now on all the functions that we've written, but I did find something that I want to change, which is our clear function that clears the target. I called it clear a few moments ago. I want to call that clear target. Just calling it clear I don't think is specific enough. We want to know when we call that function from one of our child states that we are actually clearing a target and not just clearing the entire state machine. So before we can really finish off the functions of this base class, we really need to flesh out the functions of our AI state base class. And we're going to need to implement quite a few methods here that is going to establish the way that the state machine is going to communicate with its child states. So the first method I'm going to add is going to be a public method, and it's got a void return type, and it's going to be called set state machine. And this is going to take a parameter of AI state machine. And this function is going to be called, and I'm going to add it in a moment, to the start function of our AI state machine, so that when we fetch all of the states and we add them to that dictionary, just before we do that, we're also going to call that state's set state machine function and send in the state machine's reference so that each state has a reference back to its parent state machine. And in fact, in our base class, we'll even create a protected field of type AI state machine, and we'll just call that machine. And that's where that value that we pass into the set state machine function is going to be cached. So we might as well just implement that function inline by saying machine equals machine. And from that point there, actually I'm going to call that state machine, I think. Yeah, and that parameter. It just makes things a little easier to read a little bit later on. It's surprising when you come back to code after many months how none of it makes any sense anymore. Been there a few times. Okay, there we go. So we've now implemented another function called setStateMachine, and if I save that off, we can now go and add a call to this function in the start method of our AI state machine. Remember, in our start function we get all of the AI states from our game object, and then we iterate through each one and we add them to the dictionary. After adding them to the dictionary, we'll also say state.setStateMachine, and we'll send in a reference to ourselves. Remember, it's the state machine that's calling this function, so we're saying I'm sending you me as a parameter, and then each state will store a reference to its parent state machine. So now I'm going to start adding a lot of the methods that need to be implemented in this AI state class, but they're not really going to do anything in the base class implementation, so I'm just going to create kind of empty functions so they become default handlers. And I like doing this so that when I derive a new class from AI state, I'm not forced immediately to implement every single function, even if it's one that I'm not using yet or I don't care about. So let's talk about some of these handlers. I'm actually going to call these default handlers because they are what I call handler functions, in that they are called by the AI state machine when information needs to be passed to the current state. So the first method is going to be a public. We make this virtual so we can override it, a void return type, and it's going to be called onEnterState. Takes no parameters, will have an empty function body. When we implement the update function of our state machine in a moment, you'll see that whenever we need to enter a state for the first time, this is the function that will be called, and it will give that state a chance to initialize any of its variables, so it's ready to be transitioned to. And likewise, on the other side of the fence, we need an onExit state as well, so that the state has a chance, if it needs to do any cleanup. Once again, I will make that an empty function body. And then in our update function of our state machine, it's going to take the currently active state and say, hey, it's time for you to update yourself. So we're also going to create a handler, once again, a virtual void signature, which is going to be called onUpdate, like so. Once again, a completely empty function body in the base class implementation. Now the next one's quite an interesting handler. You'll remember a few lessons ago we had Jill running around with root motion, and one of the functions of mono behavior that we overrode to accomplish that was a function called onAnimatorMove. And if we implemented that function in a script on a game object that had an animator, the root motion wouldn't be automatically applied to the game object, but instead that onAnimatorMove function would be called. Now I don't want all of my individual states to implement that function, because it means that Unity is going to be calling it on all of my scripts, even ones that aren't the currently active state. So for things like this, and I do the same thing for trigger messages as well, I only trap that in the parent state machine, and then I send them into the currently active state using function handlers that I define. In the state machine, it is going to have an onAnimatorMove function that's going to be supplied by Unity with the root motion from the animation, but that's going to send it into the currently active state only by using a function called onAnimatorUpdated. So we'll create that one here as well. Once again, all of these I think will be public virtual voids. We want the ability to override them, and they need to be public so that the state machine can call them. So I'll call this onAnimatorUpdated. Takes no parameters, and once again has an empty function body. So from an AI state perspective, you can really think of this as being like the onAnimatorMove function. This isn't automatically called by Unity, but it's called by our state machine in exactly the same place. So if in a particular state you wanted to override root motion, this is the method that you would put it in and override from the base class. Now we haven't spoken about this, but when you use humanoid avatars, Unity has a really cool IK system that allows us to do things like say, I want your head to look in this direction, or I want your left arm to reach up, and we can all do that via our scripts. And in some of my states I actually do that so that when the zombie is heading towards the target, even if it's running at an angle to the target, its head is going to be sort of vaguely looking in the right direction. If you want access to this information in a monobehavior, you just need to implement a function called onAnimatorIK, and then Unity will call that function, and that will be at the exact time that you're able to then issue commands to the various body parts of the avatar. Once again, we're not going to override that in all of our states for exactly the same reason. We don't want that function being called even in the states that are not the currently set state. I don't want to have to worry about always enabling and disabling the behaviors either. So we're going to implement that in the state machine, and then any information is going to be passed down into the state via its onAnimatorIK updated. Okay, so I'm going to implement that function too. So really the actual state machine is nothing more than a kind of message pump, really, that pumps a lot of the stuff down to the currently active state. And we're going to see how we use that later on. I think I used that in the pursuit state. And for the same reasons previously discussed, I also don't implement onTriggerStay, onTriggerEnter, and onTriggerExit methods in my states either. I use a similar method. I create my own custom function that the animation state machine can call and pass that information down to the currently active state. So this particular method is going to be called onTriggerEvent. Remember, this isn't anything that's called by Unity. This is going to be sort of my own function. And rather than having enter, stay, and exit versions of this function, I just have one onTriggerEvent function, and then I'm going to create like an AI trigger event type enumeration. So I'll make the first parameter a member of the AI, what shall I call it? AI trigger event type. Obviously, we haven't created that enumeration yet. I'll do that in a moment, and I'll call that event type. And this will contain basically just three members: enter, stay, and exit. So really I'm just mirroring what Unity's onTrigger functions do. I'm just combining them into one method and using an event type to describe to the method whether this is a stay, enter, or exit event. And the second parameter will simply be the collider that generated the event. That's not our collider, that's the collider of the thing that is colliding with us, or in this particular case, with our sensor trigger. But I'll talk more about that in a moment. And I think probably the last method that I'm going to add to this base class, for now at least, is going to be a method that is called by the state machine when the zombie has reached its target, when it's penetrated its target collider. So I'm going to call this onDestinationReached, and it will take a boolean that means if it's set to true, we've reached the target, and if it's set to false, then we're letting the state know we are no longer at our target, something has changed. There's a new target, for example. So I'll call this onDestinationReached. It's going to have to take a boolean parameter, and I'll call that parameter isReached. And once again, in the default implementation, it does nothing. Now I need to get rid of that red line. We need to define the AI trigger event type enumeration. I'm going to put all of the enumerations to do with the AI state machine and all of its AI states at the top of the AI state machine C# file, okay, rather than spread them around. So this is going to be a public enum called AI trigger event type, and it's either going to be enter, stay, or exit. If I save that off, then go back to my state file, yes, now all looks good. So let's go back to our AI state machine and now add a protected member of type AI state, because remember we have the AI state type, but this is just an enumeration. This AI state machine is also going to need to cache a reference to the current AI state that it's fetched from the dictionary. So we'll put this in our protected members, and it'll be a protected AI state, not AI state type, and we'll call this current state. And we'll set it to null by default. And then down in the start function, after we've added all of our states to the dictionary, we better try and get the initial state out of that dictionary to use as the current state. And you will remember that we have this AI state type, where is it here? And that's going to show up in the inspector. So if it was set to AI state idle, then what we want to do at the end of our start function is see if the current state type, AI state type idle, is in our dictionary, and if it is, fetch that state and set our current state to reference that particular state. But like I said, we can also set this in the inspector to anything else. So if we wanted to set this to AI state type patrol, for example, then in our start function we will fetch the patrol state from the dictionary and we will assign that to current state instead. So let's scroll down to the bottom of our start function and say if states, which remember is our dictionary, which at this point will contain all the states because we've added them up there, contains key, And remember, the keys in our dictionary are actually the AI state types. So we can send in our current state type member. So in other words, if what we've set the current state type to in the inspector exists in the dictionary, then let's fetch it from the dictionary and assign it to our current state. So we'll say current state equals state's current state type, like so. And we should also handle the case, I suppose, where we may have set the current state type to something that doesn't actually exist on the game object and therefore isn't in our dictionary. So in that particular case, it's our error. We've assigned a current state type, a type that doesn't actually exist in our dictionary. So in that case, I think we will just set current state to null. So let's now add our update function. And we'll put this after the fixed update function. And once again, we'll make this a protected virtual void function. We can override it if we want. This function is obviously called by Unity each frame, so that the AI state machine can do its thing. And one of the things it's going to do is it's going to let whatever the current state is have a chance to update itself. So the first thing we better do is just check that current state isn't null. And if it is, then we'll simply return. We'll do nothing. There's nothing we can do to send messages into a state that doesn't exist. And then what we'll do is we'll say current state and we'll call its onUpdate method, like so. However, what we wanted to do, if you remember back to our pseudocode, is we actually want this onUpdate method to actually return an AI state type so that we can compare it against our current state type, and then we can determine in this update function whether it's time to transition states. So what I'm going to do is I'm going to go back to my AI state class and I'm going to change the return type of the onUpdate function to AI state type, like so. Now this changes things because we don't really want the base class returning any state type that it isn't. It wouldn't be a good idea to just say, well, we want the base class implementation to always return AI state type idle. So I think this is a function that we should perhaps move the default implementation of and make it an abstract method. So it has to be overridden in the derived class. So I'm going to take that out of there and move it down into our abstract methods list, like so. Oops, I spelled that wrong, haven't I? There you go. So now, when we go back to our AI state machines update function, we can say AI state type, and we'll say new type equals, and then we'll call the current state's onUpdate method. And if the current state decides that it's time to transition to another state, then it's going to return that new state type, and we'll say, hey, this is different from our current state type, and then we'll transition into that new state. But in the case where the current state wants to continue functioning, wants to continue having focus, it will simply return its own AI state type. So now what we have to do is we have to compare the state type returned against the current state type. In fact, I think I'll call that local variable new state type. And then I'll say if new state type doesn't equal current state type, well then, hey, we know it's time to transition. So we'll declare a local variable called AI state new state that we'll store the new state in when we fetch it from the dictionary. Set that to null by default. So what we need to do now is see if that new state type that's just been returned by the current state is a key that exists in our dictionary, and if it is, then we want to fetch it out. So we can do the test and fetch it out in one go by using the try_get_value method of the dictionary, and it looks like this. We say if states, which remember is our dictionary, try_get_value, and as the first parameter we pass in the key of the state that we're trying to find, which of course is the new state type returned from the current state's update, and as the second parameter we pass in the variable that we would like that reference to be stored in if it's found, which is our new state local variable here. So we say out new state, like so. So what this function does is it first checks, just like the contains key method does, to see if this key exists in the dictionary, and if it does, it will automatically populate our new state local variable with the actual AI state reference, so we then have it. And of course, if it doesn't find it in the dictionary, this code in this conditional block here won't be executed, because the try_get_value will return false. So if we step into this code, it means we were able to find the correct state. So what we need to do, because we're about to change states, is tell the current state now that, hey dude, we're about to exit you. So we call it onExit state handler. And that will give that state a chance to do any cleanup that it may want to do. We will then tell the new state that we've just fetched from the dictionary that we're about to transition into it. So we will call it onEnter state handler. And finally, as this is now our new current state, we will assign our current state member to that new state. And there you go. That is how the update method transitions from one state to another. It's that simple. This is a pretty good design pattern. I've used it in a lot of games. not just to do with AI, but just for managing just objects of different types in general. In the PackDude game that I developed years ago for Game Institute, I used this whole model. I called it game state objects at the time, where instead of it being like an AI state, each state was like a section of the actual game. So it didn't matter whether it was like the main menu state or the high score state or the main game state. My main program loop could just say, current state, render, current state, get input, etc. So it's a good model to use, not just for AI. So I think as a little backup here, what I'll do is I will copy and paste this code for use as a conditional, just a fallback in case the current state that we tried to find isn't found, and we will just do one last stab at trying to get an idle state out. And this can happen quite frequently during development. For example, if one of the first states I wrote after the idle state was the patrol state, then there might be certain conditions that happen in the patrol state that might transition me into a pursuit state. And I might not have written the pursuit state yet. So I don't want everything to crash and go haywire when I want to test that patrol state and it returns a state type of AI state type pursuit. So what we'll do is we'll say if it returns a state type which isn't on this object, it isn't in the dictionary, then we'll just default to the idle state. And then all we have to worry about really is just making sure that we always at least have an idle state on our game object. And that's never going to be a problem because idle states are normally very simple and only a couple of lines long. So if we were unable to fetch the state that we wanted, we'll try and fetch just the idle state instead. And we do exactly the same thing again. We exit out of the current state, we tell the new state we're about to enter it, and then we assign that new state as our current state. And that's all we really need to do in the update method, so I think I'll put some comments in there. There you go, looks better. Just says, called by Unity each frame gives the current state a chance to update itself and perform transitions into other states. Oops, I've just noticed that first line is supposed to say if not current state. Actually, to make it a bit more clear, I'll say if current state equals null. This code never would have been executed if we had a valid state. So only if the current state is null do we return. And finally, inside this sort of conditional code block here where we've changed state, we don't just assign the state, we also need to assign the new state type as well. Otherwise, when we come back into the function, we would have changed the state and we wouldn't have changed the actual state type. So we say current state type equals new state type, like so. I have just had a thought actually. If I go back up to our start function, I've made a bit of an error there. Well, not an error, more of an oversight. You can see that once I've fetched the current state out, I should really call its onEnterState method immediately to give it a chance to initialize itself, or otherwise the very first state that we start off in will never get that onEnterState call. So I will say current state onEnterState, like so. So time's moved on quite a bit. We've got a lot of code written, but we've got literally nothing we can execute yet because we're still working on our base classes. But I think you've got quite a lot to chew on for the time being. So I think what I'll do before I finish up is I'll just show you something that I do in situations like this where I'm working on a base class that I can't actually drag onto my object yet because it's an abstract class. And I haven't created a derived class, so I can't really see the properties showing up in the inspector. Now, in the case of the AI state machine, although it's an abstract class, there aren't any abstract functions, which means all we have to do is derive literally a class from it and add nothing to it, and we'll be able to add that derived class to a game object to see what it looks like. And we know that eventually we're going to want to derive our own AI zombie state machine class from it. So let's create that script now. So I've created a new C# script. I'll call it AI zombie state machine. I'll open that up in MonoDevelop, and I'm going to change its base class. We don't want this being derived directly from MonoBehavior. We want it to be derived from our AI state machine, because this is going to be a specialist state machine that has extra stuff in it that only pertains to zombies. And like I said, because everything in the base class at the moment is implemented, there's no abstract functions, I can just literally make this an empty class for now, save it off, go back to Unity, select Jill, or more precisely, Jill's AI entity game object, which remembers the object with the collider, the rigid body, the nav agent, the thing that actually moves. I'll close all those up so we've got more inspector space to play with, and then I'm just going to drag my AI zombie state machine script directly onto her. And as you can see, we can see our current state type already. These are just the parameters that are serialized from the base class. And here we can drag in our target trigger and our sensor trigger, and there we have that nice slider for our stopping distance. So actually we might as well leave this script on her even when we're working on the base class, and I'm going to hook up those two triggers. So I'm going to drag over the target trigger first, which is this one here, and drop it in the target trigger slot, and I'm going to drag over our sensor trigger. Remember, our sensor trigger is that great big mama, which is going to be the thing that causes all the notifications about visual and audio aggravators. And I'm going to save that off. And it doesn't do anything yet. If I press play, nothing will happen. But we have written a fair bit of code, and we've got a long way into creating our AI system. So we're going to be able to really hit the ground running on the next lesson. So thanks very much for lending us your ears, guys. I'm not going to give away the scripts yet with this lesson. I'll probably wait till next lesson because at the moment they're incomplete. And frankly, you know my opinion. I think you should be following along with me anyway, pausing the video and typing this stuff in for yourself so that you really get into your brain where everything is, what all the functions are, and where everything lives. So I'll see you next time, folks. Bye-bye.